Hello, this is number 11 on the practice final. We're given the transfer function h of z of a discrete time LTI system, and for part A we're asked to find the difference equation for the system. So we know that the transfer function h of z is equal to y of z divided by x of z, where y would be the output and x is the input. So let's go ahead and FOIL this out right here. So we get 1 minus 1/4 z minus 1 . So nothing special there, I just FOILed it. 1 times 1, 1 times 1/4 times z to the minus 1 there, 1/2 z to the minus 1 times 1 there, 1/2 times negative 1/4 z to the minus 1. We get it right here. Okay, so now we can write, we're going to bring this up here, so 1/2 minus 1/4 is positive 1/4, so 1/4 z to the minus 1 minus 1/8 z to the minus 2, and we're going to multiply, we're cross multiplying here, so this is x of z. So now let's take the inverse z transform. So we have time shifting property going on here. We know that x of n minus n naught maps to z minus n naught x of z. So multiply this y through here, and we see that we have time shifts on 2 of the factors. So we get y of n, cross this one out, that's taken care of, plus 1/4. We have a time shift, so y of n minus n naught, in this case n naught is 1, minus 1/8. We have a time shift here, in which case n naught is 2, equals x of n. This is just the generic z transform, since we don't actually know what it is. So that's part A. Part B asks us to find the impulse response, h of t, if it's a right-sided signal, and it asks us if it's causal, if so why. So we're given h of z this is from the problem statement right here. So now we want to get it into a form we're more used to, so we're going to use partial fractions. Okay, so you can do this any way you want. This is the way I do it. I'm going to say if z minus 1 equals 4, then let me write it a different way. I'm going to cross multiply, so we get a 1 minus 1/4 c minus 1 plus b. So if z equals 4, then this would be 0, and b would be 2 plus 4 divided by 2 is 2, so 2 plus 1 is 3, so b would be 1/3. If z equals minus 2, then this term would be 0, and for here we would get 1, we get 1 times 1 times 1/2, yeah. I'm sorry, 1 plus 1/2, so that's 3 halves. So that implies that a is 2/3. So now we can write h of z is equal to 2/3, 1 plus c, 1 plus 1/2, c minus 1 plus 1/3, 1 minus 1/4, c minus 1. Okay, so this told us that it was a two-sided signal, so that means the region of convergence is going to be an annulus, which is a fancy way of saying a ring in a ring with some sort of two-dimensional thickness in math. So it looks like this. This is an annulus. So we know that our region of convergence is going to be an annulus. We have a pole at z equals 4 and z equals 1/2, so this would be greater than 1/2, and z is less than 4 because it's a ring. So did I get that right? Sorry, I did that backwards. The region of convergence for this one is going to be z greater than 1/2 And for this one, it's going to be z less than 1/4, so our region looks something like this. Alright, so that was 1/2, 1/4. So they wanted to know if the system is causal, but the system is not causal because our region of convergence is inside the interior of the annulus, and the region of convergence of a causal system is exterior to the outmost pole of the annulus, so it would have had to be out here, region of convergence, but that's not what we have, so the next question was asking about stability, but it's not stable because it doesn't include, our region of convergence doesn't include the unit circle, which is out here at 1. Okay, part C asks us find the impulse response if it is a right-sided signal. So we have again h of z (2/3) 1 plus 1/2 z minus 1 plus 1/3 1 minus 1/4 z minus 1. We found this in part B. It doesn't change for this one. This one says that it's a right-sided signal, so the region of convergence is going to be to the right of our rightmost pole, which is this one. Z is going to be greater than 1/2. So the system, they want to know if it is causal. The system is going to be causal because the region of convergence is, I said rightmost pole and then outermost pole. This is 1/2. We have a pole there. Our region convergence is outside, so it fits the definition. So it is causal. The next one wants to know if the system is stable, and the system is stable because it includes the unit circle, which is somewhere like right here. That's 1/2, that's 1, so it does include the unit circle. And in both part B and C, they also wanted us to find the impulse response h of well, in the question it says the impulse response h of t. That's a typo. It should be h of n because we're in discrete time. The Z transform deals exclusively with discrete time, so that part is rather straightforward. We have already done it in the review videos. You're just going to go to the table and get the correct transform, and it's also in the written solution, so I don't want to waste your time doing that. Part D tells us that it's a left-sided signal, and then we have to check for causality and stability. So again, h of z So in each of these cases, our poles aren't changing, just our region of convergence. So if it's a left-sided signal, the region of convergence is going to be is going to be less than 1/4. So the region of convergence is going to look like this. And that's a pole, and we also have a pole at 1/2 at -1/2, sorry. So our region of convergence is inside. It asked us if the system is causal, but it's not causal because the region of convergence is inside of the circle, and we know for a causal system, the region of convergence is exterior to the outermost circle, so it's not causal. The other question was if it's stable, but it's not stable because the unit circle, which is always included in the region of convergence for a stable system, is all the way out here. Well, that's more like the unit ellipsis, but this is supposed to be the unit circle. So it's not stable. So again, as with B and C, go ahead and find h of n from h of z. It's straightforward. You have the conditions, look it up in the table, and good luck on your exam to everyone.